Welcome everybody to this 2-hour tutorial at Transform 2021. This is a virtual conference of the Software Underground. Thank you very much to Studio X for supporting this conference this year. It means a lot. There's information about the tutorial you're about to see in the description below this video, so go check that out. There are some links and things in there that you need to know about. If you're watching this live, you might want to get involved in the chat, which is over on the Software Underground Slack. So go to softwareunderground.org/Slack, and you can join the Slack there. It's completely free, open Slack. And there's a channel in there called T21 Thurs Harmonica where the chat's happening. So do jump in there. And yeah, I think with that, I'm going to hand over to Santiago Soler, who is a developer on the Fatiando project, and he's going to tell you about processing gravity data with Harmonica. So, Santi.
Thank you very much, Matt. And yeah, and thank you and Software Underground for letting me do this tutorial today. So we are going to see some little code on how to process gravity data with Harmonica. As you said, my name is Santiago Soler. I'm from Argentina. I'm a PhD in geophysics. I'm a PhD student in geophysics, and we are 3 instructors today. Although I'm the main speaker, you can find Andrea, Balza Morales, and Agustina Pesce in the Slack channel. So if you have any question or you face any problem with the software we are going to share to you today, please ping them there. They are ready to answer your questions. So first of all, we have a repository for this tutorial. It's on the Fatiando GitHub organization. Again, here you can find the address, the URL. It's github.com/fatiando/transform21, and it looks like this. Here you will find the notebook I will share to you today. It's the process-gravity. And here you will find some information about this tutorial and also some instruction about how to set up the environment you'll need today for run all the code we will be writing. So you don't need to be an expert in Python programming language for follow this tutorial, but just if you have some background and know something about NumPy, Pandas, Xarray, and Matplotlib, that would be awesome. And well, here are the instruction for setting up the environment for installing all the dependencies and running the notebook. So if you want to pause this video and take the time to go through all these instructions, feel free to do so. But if you run into a problem while creating the environment, or if you don't have the time to do so and you want to follow along and you don't want to pause the video, we have 2 backup plans. The first one is that we created a Google Colab notebook. So you can run the notebook here, and it has a cell for installing all the dependencies you might need. And thanks to Filippo, we had Jupyter Hub instance in Software Underground, so you can log in with your Slack credentials, and there you will find the environment already installed. So if you want to run that, just log in and run and start a notebook on the T21 Thurs Harmonica environment. That every dependency is already installed in there. Just a warning, it's in experimental phase, so if you expect some issues, that could happen. So let's get started with the tutorial. So as I said, any questions you may have, please write in the Slack channel. And also, we are planning to have some office hours tomorrow at 11 a.m. GMT at the Chateau. and you can find a link on the Chateau in the Slack channels. So if you have any further questions, you want to discuss something else, you want to bring new ideas, you want to collaborate, or you have any other use case for Harmonica and all the Fatiando libraries, please join there and we can talk about that. So thanks again to Software Underground, Studio X, and Agile for the support. So what is Harmonica? Harmonica is one of the libraries of the Fatiando Terra project, developed by Leonardo Ulleda initially. So today we'll be using Harmonica for all the processing gravity, but we will also be using some of the other Fatiando libraries, such as Boule, that lets us define some reference ellipsoid that we will be using for computing normal gravity data. For computing normal gravity. And also we will use Verde, which is a library designed for some very fancy interpolations. But instead of using the interpolation part of Verde here, we will be using most of the functions for managing and processing coordinates and data. And you can see a tutorial on Verde that happened last year in the Transform 2020. So if you want to take a look at that, you can find that in the Software Underground YouTube channel. And finally, but not least, we will use Pooch, a little library from Fatiando that let us download or fetch, as we like to say, all your data files that are stored online. So we will use that for fetching all the data files we will use today. So you don't need to download anything by hand. We will just do that in the code. So what are we going to do today? We will focus on the Bushveld Igneous Complex area that is located in South Africa, which is the largest layered igneous intrusion within the Earth's crust. And the idea is to grab some gravity data around this area and try to see how we can process it to get some residuals, disturbances, in order to see if we can see the expression of this intrusion in our gravity data. So one thing we have to notice here is that the Bushveld is divided in 4 lobes: the northern, the far eastern, the eastern, the southern, and the eastern lobe. So just keep that in mind. Oh, I have to mention this picture. This awesome picture is made by Webb and the other authors, and has been published in a paper of 2004. So if you want to take a look at that, just look for that in the internet with your favorite search engine. So what's the roadmap for today? First, we will start by loading the gravity dataset of South Africa. Then we will slice it to keep the data that is surrounding the Bushveld Igneous Complex area. Then we have to project this data because it's given geographical coordinates, and we want to transform it to plane coordinates. And for that, we will use PyProj. That is a library for managing projections, but we'll see that later. Then on the 4th step, we will compute the gravity disturbance by removing the normal gravity from the gravity data. And we will do that through Boule. Then we will load a digital elevation model of the survey area that we have. I have created through eTopo1, and use this elevation model to create a set of prisms that drapes the topography, and we'll use that to compute the Bouguer gravity disturbance. Then we will take a break of 10 or 15 minutes, and I expect that we will be running some code in there that might take your computer quite busy. So we'll take just a break for you to run this this heavy computational process. So when we come back, we will interpolate the Bouguer gravity disturbance we just computed with the equivalent layer technique. And finally, I want to show you how we can obtain a profile of the Bouguer gravity disturbance by, instead of extracting the profile from the interpolated grid, we will use the same equivalent layer we used in the previous step to do so. So let's get started by importing some libraries. First, I will import some libraries that you might be familiar with. I will start with NumPy, so I will type import NumPy SMB. Then I will import Xarray. If you don't know Xarray, it's a library for managing multidimensional data that it's very awesome library, which is based on NumPy, as Panda is based on NumPy. So that we will import Xarray by import Xarray as XR, and then we will import matplotlib, and particularly pyplot as PLT. So that's import matplotlib.pyplot as PLT, and we will use PyBrush, as I said, for managing projections. So let's import PyBrush. Sorry, have a, okay, no. So you may be familiar with these libraries. Now let's jump to import the Fatiando libraries that we will use. First, let's start with Puch by importing Puch as it is. Then we will import Harmonica, as HM. So remember, every time we type HM, I'm using Harmonica. We will import Boule, as BL, and import Verde as BD. So it's okay if you don't remind all these aliases. I will mention them as I type. So let's run this cell to import all the libraries. And I will do something here so you can see all the figures bigger. You don't have to write this if you don't want. So this is just for you to see the figures in a larger size. Okay, so let's move on. So let's start by loading the dataset. Okay. So let's to load the dataset, the South Africa dataset that we want to use is a dataset that has ground measurements of the gravity, and we can use Harmonica to fetch that because it's already as one of the sample datasets in Harmonica. So I will store this dataset in the data variable, and we'll fetch it from Harmonica hm.datasets.fetch _South_Africa_gravity. So as you have seen, I have to type everything, but I don't really have to because I can use the auto-completion by pressing tab on Jupyter Lab. So I will do that more often in the future. So if you see that some function name suddenly pops up, it's just because I pressed the tab, just in case I'm not doing some dark magic here. Okay, so, and let's see what the data variable has if we do this. So I'd already have this data set in my computer, but in your case, if you're downloading this for the first time, you will see a notification that it's being downloaded and where it's stored. So it's just a cache folder in your personal folder. So this data contains 4 columns. So it's a scatter points in latitude and longitude. of absolute gravity data. This is observed gravity. And it has also the observation height of each of these observations. So, and that's something we will talk about in the future. So take into account that we have a longitude, latitude, and also elevation for this data. So let's see how this data looks. So let's plot it with matplotlib. And because these are scatter points, I will use the plt.scatter function to do so. And we'll store the output of this scatter function into a tmp variable. So let's type tmp equals plt.scatter. And let's call that by passing the longitude and latitude in the x and y axis respectively. So that would be data.longitude, comma, data.latitude, comma, and let's paint the dots in the scatter points by using the value in the gravity column. So to do so, I have to type c equals data.gravity. And I will change the size of the dots because they are, by default, they are too big. So I would put s equal to 1. And then I will do some stuff that will be repeated through the notebook. So I will explain it very well here, but in the future, if I just type it, remember that it's the same thing I'm writing here. So one of the things I want to do is I want the x and y axis to be in the same scale. So I have to change the aspect of the axis. So in order to do so, I can get the current axis by the function plt.getCurrentAxis that g say ca, and then I will call this function, and then I put a dot set underscore aspect parentheses quote equal. So with this line, I'm setting the x and y axis with the same scales. Then I will add some color bar with plt.colorbar, and I will pass the tmp variable we define in the first line of the cell, and add a label because all this data are in milligal. And let's hit enter here. Sorry, shift enter. To run the cell in JupyterLab, it's shift enter. So as you can see, we have all the gravity data in South Africa. This covers the entire country, but the region we want to focus on is right here. So we want to cut this data set around this area. So to do so, we'll use a Verde function called inside to get a mask of the points that are inside this region, and then use this mask to cut the data set itself. So let's define the region we want to cut the data set on. So I will call that region underscore DEG equal, and let's put these values for longitude and latitude. I want to cut it from the 25 degrees longitude up to the 32 degrees longitude. And in latitude, I want to cut it from the minus 27 degrees up to the minus 23 degrees, okay? And as I said, I will use the Verde dot inside function to cut, and I will store the output inside. I will store the output in a variable called inside. So I will use Verde dot inside parentheses, and remember that in JupyterLab you can press Shift Tab to see the signature of the function. So as you can see, this function requires two arguments: the coordinates we want to cut and the region we want to cut these coordinates on. So let's pass the coordinates, which is a tuple of the longitude and latitude, and as a second argument, we will pass this region underscore dig. Okay, so let's put a tuple with the data.longitude, and the data.latitude, and then the region underscore DEG. And okay, so let's see what the inside variable has inside. So this is a pandas series. We has booleans inside that mask all the points that are within the region of interest with a true, and all the points that are outside this region with a false. So how we can cut our pandas data frame? We can just define data equals data bracket inside. And by doing this, now we have almost 4,000 points, while originally the data set has almost 15,000 points. So we actually kept this data set around the region of interest. So let's plot this this cut dataset, and we will do the same as we did before. TMP equals plt.scatter, and inside I will pass data longitude and data latitude, and I will paint each one of the scatter points with the data.gravity, and I will change the size of the dots to 1. I will change the aspect of the axis with plt.gca.set_aspect, and I will pass a string equal, and I will add a color bar here by passing the TMP variable and adding a label because the gravity is in million. So pressing Shift Enter, I run this, and as you can see, we actually have cut the data in our region of interest. So before we follow along, let's project the data into plane coordinates. So let's write this. Sorry, project data. So to do so, we have to define a projection that we want to use. For example, let's use the Mercator projection. And we can do that by defining a Proj object through PyProj library. So let's define projection equal PyProj.proj with a capital P. And then we should pass, we'll pass 2 arguments. First, the projection we want, that's proj equals and quote merc for Mercator, and then we will pass the central latitude of this projection as the mean value of all the latitude points. So that would be lat_ts equals to data.latitude.mean, and let's call this method because mean is a method. So by doing this, we are actually defining the projection, but we are not projecting the coordinates yet. So to do so, we have to call this projection by passing the longitude and latitude values of our data. So all the input of this of the calling of the projection object would be longitude and latitude, and the output, we will call that easting and northing. So that would be easting and northing equals to projection and parentheses, and then here we will pass 2 arguments, the longitude and the latitude. So that would be data.longitude and data.latitude, okay? But we have to do something here because PyProj doesn't really like to work with pandas series. So we have to put actually the NumPy array that are stored inside the longitude and latitude columns. So to do so, we have to put dot values and dot values here, okay? This is a minor detail, but keep that in mind. So if we run this, we will be actually projecting the coordinates. And let's, instead of having the easting and northing variables playing all around our notebook, let's store these easting and northing variables inside our pandas data frame. So we can do that by assigning these easting and northing variables to new columns inside our data frame. So we can do that by typing, data equal data.assign, and let's call this method with easting equal easting, and data equal data.assign parentheses northing equal northing. Okay, so if we do so, let's see what happens to a data variable. As you can see, it's the same data frame we had before, with the 4 original columns cut in the region of interest, because here that's why we have 4,000 points. But we also now have the easting and northing columns, which are the projected coordinates of the corresponding latitude and longitude, and these two are in meters. Okay, that's why we see a very high power here. It's to the power of 6. Okay, so let's now generate the same plot we did before, but instead of using longitude and latitude, let's use the northing and easting. So we can do that by typing tmp equals plt.scatter, and now instead of passing longitude and latitude, we will pass easting and northing. So that would be data.easting and data.northing. And again, we will color the points with the gravity data. So that would be C equals data.gravity and S equal 1. Let's change the aspect of the axis with plt.getCurrentAxis underscore aspect. Call this and equal. And add a color bar, plt.color bar, with the tmp variable as first argument, and then the label of millical. Okay, so I run this all with Shift Enter, and now you can see roughly the same figure, but now they are in projected coordinates where the x and y axis are in meters. So let me take some water. Okay, I was all into the coding part, but I want to take now the time to think about what are we seeing right now. So this is the observed gravity. That is, all the values are very close to this 979,000 milligal. And that's because we are actually seeing all the gravity signal of the Earth, which includes all the gravitational attraction of the Earth, and also the centrifugal component, the centrifugal acceleration, because the Earth is spinning around its axis. So in order to be able to see what the gravitational effect of anomalous bodies beneath the surface or above the surface of the Earth, we need to remove from this observed gravity the signal of the normal gravity. And in potential fields, the normal gravity is usually defined as the gravity effect of the reference ellipsoid. So what are we going to do here is to compute the gravity disturbance out of the observed gravity by removing the normal gravity. So let's put a title here to organize better this notebook. And so let's put compute gravity disturbance. So how can we compute the gravity disturbance and essentially the normal gravity? We can do that through Boule. Boule is one of the libraries I mentioned before that allows us to define a reference ellipsoid. So let's define one of the most famous ellipsoid you might have here or work with, that's the WGS84. So we can very easily define this ellipsoid by defining ellipsoid equal bool, that's BL dot WGS84, and it's all in uppercase. Okay, take that into account. And if we run this, let's see what the ellipsoid variable has inside. So it has created an ellipsoid object with all the parameters needed to define the WGS84 reference ellipsoid. So through Boule, you don't have to remember or manually type all these parameters for defining reference ellipsoid. It's already there. And not only that, the ellipsoid class has some very cool methods for doing some stuff. One of them is compute the normal gravity that this ellipsoid generates on any point. And by any point, I mean on any point at a given latitude and a given height. Okay, so we can compute the normal gravity equals to ellipsoid. Oh, sorry, I made a typo here. Ellipsoid, okay, dot normal underscore gravity. And let's call this. So remember, if I press Shift Tab, I can see the signature of the method or the function. So the normal gravity method particularly asks as the latitude and height of the points on which we want to compute the normal gravity. And because we want to remove the normal gravity from our gravity dataset, let's pass the latitude and height of our observation points. So we have to put data.latitude and data.elevation. Okay. And let's see what happens if I do this. Normal gravity. Okay, it returns a Panda series with all the values of the normal gravity on each one of the data points we had in the data frame. So let's, again, instead of having, so first of all, let's compute the gravity disturbance. So gravity underscore disturbance would be equal to the data dot gravity, that is the observed gravity we have in the data set, minus the normal underscore gravity. Okay, and this would be gravity disturbance. This would be also a Panda series with all the gravity disturbance values. And again, we don't want to have this variable all around the notebook and have to remember its name. So let's store this inside our data frame again, as we did with the northing and easting columns. So let's put data equals data.assign, and let's put gravity underscore disturbance equal to gravity underscore disturbance. Okay, I will have to do something here because this cell has a row type, so I have to change it to code. Okay, and now I can run this, and let's see what the data variable has once we do this. So after I run the cell, now you can see that we have the gravity disturbance column here. Okay, so let's plot it against the northing and easting values. So that would be TMP equals plt.scatter. Let's call this function with data.easting and data.northing. And now we will color the dots in the scatter. Instead of with the gravity column, we will use the gravity disturbance column. So that would be C equals data.gravity underscore disturbance. And I'm too lazy to write every time, so I will press tab here. So SjupyterLab will autocomplete. And then also let's reduce the size of these points to 1. Let's change the aspect of the axis. So plt.getCurrentAxis.set aspect to equal and let's put a color bar also, plt.colorbar, and let's pass the TMP, and also the gravity disturbance is also in milligal, so I will put a label of milligal here. So now we can see that we have values in milligal ranging from around -80 milligal to 125 milligal. So now we are actually seeing the signal of every anomalous body within the Earth, and also generated by the topography. So the idea behind this notebook is to try to see what the gravitational response of the Boule igneous intrusions are, right? So to do so, we have to remove some signals that are bothering us here to make some, to interpret this data. So one of the signals that are very annoying here in order to see the intrusions is the gravitational effect of the topography. So you can imagine that if you have a mountain below your feet, that it's all the terrain that is above the reference ellipsoid, all that mass generates a gravitational effect, and that gravitational effect is strong. So in order to actually see all the intrusions that are within the Earth, we have to remove the effect of this topography. So here in Harmonica, we have some pretty cool forward models to that will enable us to actually remove the effect of the topography. So what we are going to do is to model all the topography through rectangular prisms and compute the gravitational effect of those rectangular prisms in order to remove that signal from our gravity disturbance. Okay, so to do so, we need to have a DEM, that's a digital elevation model. Okay, so we need to have some data of how the topography changes on this region. So I prepared from eTopo1. It's just a slice of eTopo1. So I prepared a data set containing a DEM of 1 minute arc, and I uploaded to GitHub. But so we can use Push now to actually retrieve that data set to our computers and load it in Python through Xarray. So what are we going to do now? It's compute Bouguer gravity disturbance. Okay. So let's start by loading the DEM I mentioned. So I will define URL equal to, and I will write the URL to this data set. And thanks to Software Underground, I could make this URL much shorter than it was originally. So let's type https /swu.ng/bushveld. I have to write this very well. Dash topography. Okay, this is the URL for the dataset we want to download. One way would be to download manually, but we want to avoid that. So we have Push to do that work for us. So let's put fname equals to push.retrieve. And let's put parentheses to call this this function. And if I press Shift Tab, I can see the signature of this function. And it asks two main parameters, the URL and the known hash. And optionally, we can pass an fname to change the name of the file that will be stored in our computers. So for the URL, I will pass the URL variable we had defined before, URL. And for non-hash, this is for making a checksum. So Puch can download any dataset from the web, and then it can check if the file is not corrupted. To do so, we have to pass a hash to it. But because this is the first time I'm downloading this dataset, I don't know the hash. So I will pass none here. So that will tell Puch to ignore the checksum process and just download it. Okay. And let's call this with a different name. Let's put fname equals to a string called bushveld underscore topography.nc. I call it nc because this is a netcdf file. And let's run this up. So in my case, I've already had this file downloaded. So it actually returned the path to the file that is stored in my computer. But in your case, it will probably pop up some note saying that it's downloading the dataset and also noticing you that it has computed the hash. And just in case you want to use that hash in the future, you can copy that and paste it here on the non-hash parameter as a string. So just in case you want to download it again, you can do that. And also you'll be actually checking if the file is corrupted or not. So this fname, it's only a path to the DEM file, but I want to actually load it in Python. So to do that, we have to use xarray to load the netcdf files. So let's put topography equals to xarray, that's xr.load underscore dataset, and let's put parentheses, and let's put the path of the DEM file. And let's see what the topography variable has inside. So, okay, thanks, Martin. He's sharing the output of the puch.retrieve function. Okay, so what the topography variable has is an xarray dataset. It has two coordinates, one for longitude and one for latitude, and has only one data variable that is called bedrock. And as you can see, the bedrock is a two-dimensional array in the longitude and latitude coordinates. And also it has some attributes like the conventions it used, some title, some GMT version, and the DOI, just in case you want to look for the original object that created this dataset. Okay, so one thing I'm going to do here is I don't want to be actually using the whole dataset because it has only one data variable. So I will rename the topography variable to only the xarray data array that is stored within this dataset. So I can do that by typing topography equals topography dot bedrock. That's the name of the data variable. So if let's see what the topography variable has inside now. And as you can see, it extracted the data array, the bedrock data array from the dataset. So we have the data array object directly. So now the interesting part. Let's, first of all, we have to model this DEM with rectangular prisms. But rectangular prisms can only be defined in Harmonica, at least. You can only define it in Cartesian coordinates. That would be in plane coordinates. So what we have to do before actually being able to model the topography with prisms is to project the topography to plane coordinates. And we can do that by using a very neat Verde function that is called project_grid. So let's put topo_plane to define a new grid that would be in plane coordinates. That would be northing and easting. equals to verde.project_grid. And let's call this function. But let's see with Shift Tab the signature of it. And as you can see, it asks 2 parameters. First, the grid we want to actually project, and then the projection. And this projection can be a PyProj object. So what are we going to do? It's passing the topography, that would be the grid, and the projection. And let's see what the topo_plane variable has inside. It might take a while, not so long, but it depends on the computer you have. So if it takes a few seconds, just wait there. So as you can see, now we have another data array, but instead of having longitude and latitude coordinates, it has easting and northing coordinates. And all the values are like an interpolation of the original values to the now the easting and northing grid points. As you can see, it has some not a number values, and that's because these points fell on the outside of the convex hole area of the original dataset. So just to keep in mind, we have not a number values there, but it won't cause any problem in the future. So let's see what this grid actually looks. So we can plot this grid very easily with Xarray. We can put topo_plane.plot. That's it. And I will change the aspect of the axis. So that would be plt.getCurrentAxis.set to equal. And let's see what happens. So wow, Xarray plots everything for us. It even puts some labels in the axis. So we have the easting and northing values, and this is the elevation of the topography. Awesome. And this is in meters. Keep that in mind that we are working always in SI units, except for milligauss, but that's the only exception we'll make today. So finally, let's model the topography with prisms. Okay, so the idea is to model this DM with prisms. Just to have an idea of what it should look like, I will share you this awesome figure that Agustina made for us. So currently we have like this, right? We have the topography on a finite set of points, okay? And we will have to define a reference level that would be the 0 height in this case, because we want to model the topography. And we will, what are we going to do is to define one rectangular prism per each point in the grid. And each one of the points in the DM grid that we have right now will be the center of each one of the prism. So through the prism layer function in Harmonica, we can transform this data set with this reference value into a layer of prisms. That would be a regular grid of prisms in the horizontal coordinates whose top and bottom boundaries are variable. Okay. In this case, the bottom variable would be just 0, would be stick to the reference level, but you can change that if you want. Okay. So let's do that for a change. Okay. So to do so, we have to define. Sorry. Let's see what the prism layer function. Since I mentioned already, let's see what the signature of the prism layer function is. So let's type HM.prism. Layer, and let's type Shift Tab to see a signature. So it asks a few arguments. First of all, the coordinates of the center of the prisms, and in this case, they would be the coordinates of our DEM, the surface, and the surface is the uppermost boundary. In the figure I've just shared, that would be the topography itself, okay? And also the reference that, as I said before, we want to set it to 0 height. and some properties. Properties would be a dictionary containing all the properties that this prism will have. And since we are modeling topography, we'll pass only the density of the topography, okay, to 6,770 kilogram per meter cubic. Okay, so let's put first, let's forget this cell for a while. I just use it to see the signature. And let's create a new cell and create the prism center. Okay, prisms centers, that would be a tuple containing the easting and northing coordinates of the topography. So let's put topo underscore plane dot easting and topo underscore plane dot northing. Okay. Then we will define the surface array. That would be a two-dimensional array. And in this case, we want the actual DEM to be inside that. So let's put surface equals topo plane. And here we have to put the values because we don't want to be using the X array grid. We want to actually be using the NumPy two-dimensional array. So that's why we have to put the dot values in there. And then let's define the density of these prisms. So as I said before, we will use the 2,670 kilograms per cubic meter, and we will have to multiply that by a two-dimensional array full of ones. So we can do that by typing NP, that's for NumPy, ones underscore like, parentheses, surface. So we want to create a two-dimensional array that has the same shape of the surface array, but now we will multiply all these ones by the density of these prisms. This density value is like common density value used in potential fields. So it's a good start. It might change on a different area, but it's a good start here. Okay, we are having a question that I want to address because it's important. So someone asked about the Fourier correction. How does this include the Fourier correction? So before I jump into define the prism layer, I want to actually answer this question because it's very important. So let's go back to the step where I compute the normal gravity. Okay, so the Fourier correction, when we compute the Fourier correction, we take the observed gravity and remove what is called the normal gravity on the surface of the ellipsoid. And then to that, and then it's usually called gravity anomaly, all right? And then we remove the Fourier correction to get the free air anomaly. Okay, these two terms, the normal gravity on the surface of the ellipsoid and the Fourier correction, are just a first order approximation, that is a Taylor series approximation to the first order of the analytical formula we have in Boule for the normal gravity. So saying that you are computing the free air anomaly is roughly the same as saying I'm computing the gravity disturbance. The main difference between these two is that I'm computing the analytic solution of the the gravity effect of the ellipsoid on every point. Okay, so that's the difference. If I haven't explained myself very well, or if you have more question about this, we can meet in the after hours, in the office hours in the chateau. So please join, or I could answer this question later on the Slack channel and start a discussion if you want. But just keep that in mind. Okay, let's go back to where we were before. Okay, so back again, we have to model the topography with prisms. So we have defined so far the priscenters, that would be the coordinates of the DEM, the surface, that would be the DEM itself, and we have defined the density of these prisms to be equal to every one of them. So what do we have left is to actually create the topo prisms. Okay, we have to create the layer of prisms, and we will do that through the harmonica.prism layer function. And we have to pass, as I said before, several arguments. First, the prisms centers. Then we'll have to pass the surface. Okay. Third, we have to pass the reference. And as I said before, I will put a reference equal to 0. And lastly, we have to pass the density as a property. So we have to pass properties equal to a dictionary where the key would be density, okay? And we will pass the density array we just created. Density, okay. And let's see what the topo prism variable has once we run this. So as you can see, it has created another X-array dataset that has now 4 coordinates. The easting and northing coordinates are the centers of the prisms, while the top and bottom coordinates, you can see that are 2-dimensional arrays, are the surface, the top surface of the layer and the bottom surface of the layer. And inside the data variables, we have the density of each one of these prisms, which is a constant for all of them. Okay? So one thing you have to keep in mind is that all these units are assumed to be in meters and the properties in SI units. Okay? So let's jump into computing the gravitational effect of these prisms. So first of all, we want, so we can do that by using the prism layer accessor that we have in Harmonica for the X-array dataset objects. So if I type topo underscore prisms dot prism layer dot gravity, and I press Shift Tab to see the signature of this method, you can see that we can access through the prism layer accessor, we can access to the gravity method that allows us to compute the gravitational effect generated by this layer of prisms. And to do so, we have to pass the coordinates of the observation points where we want to compute the gravitational effect of the prisms, and also the field we want to compute. So for the coordinates, we have to pass the easting, the northing, and the upward coordinate. That would be the elevation of the observation points. And for the field, we'll be using the downward acceleration. That would be the G underscore Z. Okay? So let's define first, let's create another cell where I can define the coordinates of the observation points. So these coordinates would be the easting, northing, and elevation columns in the original data frame. So that would be data.easting, data.northing, and data.elevation. And let's store the result of the forward model in a result variable. Okay. So that would be topo underscore prisms dot prism underscore layer dot gravity, and passing the coordinates as the first argument, and then the field equals to G underscore Z. So before you press Shift Enter here, and before I press it, I will warn you that this step might take a while. It depends on how powerful your machine is and how many cores it has, because the forward modeling is done in parallel. So if you have more cores, it will run faster. So let's do this. Let's take this opportunity to leave this cell running and go for a break. And we can meet in, 10 minutes. So I have Yeah, I have a clock here, so let's meet in 15 minutes. Okay, so I will run the cell and let's go for a break. I have to mention, as you can see, the cell is running because I have this star here. When you see a number here, it means that the cell has finished to compute. So let's meet in 10 minutes.
So get started again at 11 minutes past the hour. Sound good?
Oh, sorry. Yes. 10 minutes past the hour. Okay.
Yeah. Okay, good.
Okay, I'm back. So I'm reading that Martin is running the Jupyter Hub machine that Filippo set up, and it's not a huge machine, so it would take some time. Hopefully less than 15 minutes. Okay. So Matt, can I continue? It's everything okay?
Yes, absolutely. We are still streaming. We're good to go. Thanks, Santi.
Okay, thank you. So my computer has finished. If yours not, you can either wait for it to finish or you can stop the video and resume when it finished. Your choice. So what's inside the result variable now? Well, the output of the gravity method is a NumPy array, 1D NumPy array. And again, so we want to compute the Bouguer gravity disturbance. And the Bouguer gravity disturbance is defined as the gravity disturbance minus the gravitational effect of the topography. So we can define the Bouguer underscore disturbance equal to the difference between the gravity disturbance we already have and the result we just computed. So that would be data dot gravity underscore disturbance minus result. And again, we don't want the Bouguer disturbance variable all around the notebook, so let's store its values inside a new column in the original data frame. So that would be data equal data dot assign parentheses Bouguer disturbance equal to Bouguer disturbance. Okay, I'm checking I haven't done any typo. Okay, it's okay. So let's see what the data variable looks now. So as you can see, it has all the previous columns we had so far, plus the new Bouguer disturbance column. And let's see what it looks like in a plot. So we can plot as we've been doing before, TMP equals plt.scatter and easting, data.northing, and let's color each one of the scatter points with the Bouguer disturbance. So that would be data.Bouguer disturbance. And let's resize the dots to 1. Let's change the aspect of the axis. So plt gca.set aspect to equal. And let's add a color bar. Okay. So plt color bar TMP label, and again the gravity disturbance is in milligal, so that would be milligal. And let's see what happens here. Okay, so now we have values, so many values negative and a few positive. And since I haven't mentioned this before, but since we are seeing values that are around 0, what we can do is change the color map to something more representative of values that are negative and positive. So we could change the color map to, for example, one I really like, that is the seismic color map. So here in the scatter function, I could put another parameter called cmap equal to seismic. And if I plot this, I use a color map that goes from the blue through the whites and then through reds. Okay, but the problem here is that the color map is not centered around 0. So what we can do is pass the minimum and maximum values for the color map to be in module equal. And that value should be the maximum absolute value of the data we are plotting. And we can get this maximum absolute value through NumPy. I'm sure you will manage to do that very quickly. But we can use a Verde function called maxAbs. So we can obtain the maxAbs variable as the output of the Verde docs maxAbs and pass the Bouguer disturbance. And that would be data.Bouguer disturbance. And then pass the vmin equal to minus the maxAbs and vmax equal to maxAbs positive. And if I run this cell now, I get the color bar to be centered around 0, and I can actually take a look at the scatter plot and see the sign of the values. So as you can see, the Bouguer disturbance has a lot of negative values. Okay, and the reason behind it is mostly, in most cases, is that we have removed the signal from the topography. But if you have topography, you have a root that is within the mantle. So this root has a negative density contrast that creates a negative disturbance. So what we can do to try to remove this effect is to remove the regional trend we have in this map, in this scatter plot, right? So so again, our goal is to get the gravitational response of the intrusions. So we don't care about what happens in a regional sense because of the roots of the Horowitzic discontinuity. So let's remove the regional trend from this data set by adjusting a polynomial trend of second degree. Okay, so we can do that using Verde. We can define the trend. Oh, sorry, I have to change the cell to code and then actually write in the cell. So we can define the trend to be an instance of the Verde.trend with capital T object, class with a degree of 2. Okay, so here we are not computing the trend of the data, we're just creating the trend object with specifying the degree of the polynomial to a number 2. So what we can do is fit this object with our data. So we can put trend.fit, and with Shift Tab, I can see the signature of, I have to run this, right? Yeah, so let's remove this, run the cell, create a new cell, and put trend.fit. And I press Shift Tab, and I can see the signature of the fit method, which asks me to pass a set of coordinates, a data, and optionally weights, but we won't use the weights now. So for the coordinates, we have to pass a tuple with the coordinates of our Bouguer disturbance, and the data would be the disturbance itself. So let's put for the coordinates argument, let's put the data.easting and the data.northing. And for the, we have already computed the coordinates and stored them in a variable, right? So this in this line, we have already defined the coordinates. So instead of rewriting everything, we can use this variable. Okay, so let's remove this and write coordinates. And as a data, as I said, we have to pass the Bouguer disturbance. So that would be data.Bouguer disturbance. And if I run this cell, I'm actually fitting the trend. But again, I'm not computing the trend on the data points. So what we need to do is to predict the trend on our data points. And let's do that. So I can compute the result equal to trend.predict, okay? And pass the same coordinates we use the trend to fit the trend, okay? So we'll be predicting the trend on the same data points we use to fit. And let's call residuals to the difference between the Bouguer disturbance and the regional trend. So let's put data.Bouguer disturbance minus result, and let's see what the residuals has inside. Oh, okay. I made a typo here. So the coordinate variable doesn't exist. The one that do exist is the coordinates variable. So let's run this cell again. And we have a pandas series with all the residuals here. So again, we don't want the residuals variable to be all around the notebook. So let's assign the residuals values to a new column in the data frame. So we can do that by typing data equal data.assign, and let's put residuals. Oh, sorry, let's call it Bouguer residuals to be extra clear. Bouguer underscore residuals equal residuals, and let's see what the data variable looks like now. So we have added a new column, and let's plot these values, sorry. So we can do that by typing tmp equal plt.scatter and passing the data easting, the data northing, and coloring the points with data Bouguer residuals, this one, and resizing the points to 1, changing the aspect of the current axis, and adding a color bar, tmp, and a label of milligal because we haven't changed the variable, the units. And again, I will plot this using the seismic color map, and I want to center it around 0, so I have to compute the max apps equal to verde.max apps and passing the data.Bouguer residuals. And here I will pass the color map equal to the seismic and vmin equal to minus max apps and vmax equal to max apps. And let's run this cell. And as you can see, we are getting a very cool output where we have very positive Bouguer residuals value and very negative Bouguer residuals values. So now we can start interpreting this figure by saying, okay, these intrusions must have a higher density than all the deposits that are around them. So they must show a positive gravity disturbance. Okay, and this scatter point starts to look like the figure published by Susan Webb, but we want to make it even better. We want to be able to see and interpret this figure a lot better. So what we can do to do that is to actually interpolate these scatter points into a regular grid of points, okay, which is the same as saying, let's grid the residuals. Okay, So as I said before, in order to grid these residuals, we will use the equivalent sources technique. And basically, the equivalent sources technique is based on having a set of scattered observation points and generate a set of equivalent sources that, in this case, we will use point sources beneath the observation points, okay? And what we want to do is to fit or estimate the coefficients of these sources in order that they will generate the same field that we have observed or measured in the field. And once we fit the coefficients of the sources, what we can do is to actually predict the field generated by these sources, or they are also known as equivalent layer. So we can predict the effect of this equivalent layer or sources on the coordinates of a regular grid that could be at any height. So if we can generate a regular grid that is above any observation point we have, we'll be not only gridding the residuals, but also upward continuing the residuals. Okay, that's one thing that we can do with equivalent sources. The benefit of using equivalent sources next to using a regular two-dimensional gridder like Kriging or splines is that the equivalent sources always produce harmonic fields, and they also consider the height of the observation points and the height of the coordinate points of the points where we are going to predict on. So in order to use equivalent layers or sources in Harmonica, we had a class that works almost the same as the trend class we have used before with Verde. So let's use the harmonica.eql harmonic. Pay attention that EQL and the H have to be uppercase. And let's press Shift Tab to see the signature of this class. And we have to pass some, optionally, we have to pass some arguments to it. So first of all, we have to pass a damping. The damping, what it does is smooths the coefficients of the sources. We encourage people to use damping because otherwise the sources will fit very well to the observed data, but when they are used to predict the field on a different set of points, it will create a lot of artifacts. The predictions will not be accurate. And the other thing I want to change is the relative depth. That is if I go back to the figure, that is the relative depth at which each one of the point sources will be located beneath each one of the observation points. So I want to change that also, because if we keep them too shallow, we'll be creating a lot of artifacts and inaccurate predictions. Okay, so you can play around with these two values, the damping and the relative depth, in order to get the better ones, the best ones. Sorry, I don't want to get into too much detail because I don't have time to do so. But we can continue the discussion if you want through the Slack channel, through the Fatiando Slack, or even tomorrow at the chateau. So let's pass a damping. I will choose a damping of 100, but this value can go from 1 to the -8 to 1 to 1000, for example. It's change the damping in order of magnitude, not so much on an actual value of from 2 to 3. And while the relative depth, I will put it to, in this case, 5 kilometers. So I can put 5E3 to specify that I'm adding 3 zeros beneath after the 5. So here with this line, I will be creating the equivalent layer that I will store under the EQL variable. So if I run this, the EQL is, sorry, made a typo here. EQL, the EQL is just an object that has been defined. It didn't fit the sources coefficients and nor made any prediction. But we can start by fitting the coefficients of the sources. So we can do that through the fit method, as the same as we did for the trend object. So we can type eql.fit parentheses coordinates, comma, and that's the coordinates of the points of the data points, and let's use the Bouguer residuals to fit. So that would be data.Bouguer residuals. So warning here, I will run the cell. It might take a few seconds. It would probably be faster than the forward model, but currently the EQL harmonic implementation in Harmonica allocates a whole Jacobian matrix that might be too large to fit into memory if you have too many data points and sources. So for 4,000, 10,000, 20,000 points is roughly, it's roughly safe. You're not going to break your system. But if you have, I don't know, 200,000 points, forget to do this. I will tell you more how you can do this at the end, and how my research is moving towards enabling us to feed 2 million points if you want. So for now, it's safe for you to run this cell because it's a small problem. Okay, but be careful if you are working with larger problems. So now we have fitted the coefficients of the sources. Now what we want to do is to actually use this layer to predict the gravitational effect on a regular grid. And in order to specify the regular grid, we have to pass a few arguments to it. First of all, we have to define, as I shown in the figure, we have to define the height of the hour coordinate of the grid. Okay, so one way to do that is to, for example, get the maximum value of the observation of the data elevation. So for example, we have data.elevation.max, and our maximum observation point is at roughly 2,200 meters. So let's use 2,200 meters for the height of the grid. And one thing we have to do is to define the region where we want to define our regular grid and the spacing. One thing what we can do in Harmonica is to make the grid in geographic coordinates, even though our coordinates are in Cartesian, they are projected coordinates. Okay, so even though our coordinates we use to fit the equivalent layer are plane coordinates, are projected coordinates, we can define the grid to be in geographic coordinates, which is awesome if we want to share this grid to a colleague, because we don't need to pass also the projection we use to generate those plane coordinates. We'll be passing longitude and latitude coordinates. So let's use the grid method of the EQL. So we can put grid equal, I will put the screen, okay, here. Grid equals to EQL.grid. This is a method, and we can see the signature of the method. And it asks, as we said, the upward, the region where we want to generate the grid points. Optionally, the spacing or the shape. I will pass the spacing. And the dims will be the names of the coordinates we will be passing. So in this case, I will change that to latitude and longitude. And also the data names will be the names of the data array that the grid method will create. And lastly, we have to pass the projection if we want our grid to be defined in geographic coordinates. So let's start with this. By upward, I will pass, as I said before, 2,200 meters. Okay, that's the height of the grid. The region of the grid, I will set it exactly the same as the region we use to cut our data values. So if you remember at the beginning of the notebook, that's stored in region_deg. And what else? I have to set the spacing of the grid. That would be the spacing between neighbors' points in the grid. And because now the grid will generate is in geographic coordinates, let's put 0.01 degrees. Okay, that is roughly 1 arc minute or so. We can discuss that, but roughly is that. And let's change the dims. So that would be the coordinates names to latitude and longitude. So pay attention here that this is the only place where I have to change the order of the coordinates names. Usually in the whole Fatiando ecosystem, we work with longitude and latitude, or easting and then northing. But when setting the dims, we have to use the reverse order, latitude and then longitude, or northing and then easting. Okay, just keep that in mind. If you don't remember that, because you won't remember that, even I don't remember that sometimes, it's on the documentation. So if you go here to dims, you must be defined the following order: northing dimension and then easting dimension. Okay, and let's change the data names. So data names expected to be a list, so I have to put brackets and then write a single string here called Bouguer disturbance. And finally, but not least, I have to pass the projection I want to use to recover the to unproject the coordinates. So projection equal projection. Okay, and let's see what the grid has inside. This process is much faster than the fitting process, and it doesn't need all your memory. Okay, so it's roughly a forward modeling with points, so it's fairly easy, and it's also done in parallel. So if you have a course, it will take all your a course to make it really quick. So we have this data set with longitude, latitude, and upward coordinates. As you can see, the upward coordinates are all the same. The 2 kilometers, 200 meters we defined before, and the gridded gravity disturbance. So let's plot this grid just with the X-array tools. So we can say grid.Bouguer disturbance dot plot. Yeah, that's right, plot. And let's change the aspect of the axis. So plt get current axis dot set aspect parentheses quote equal, and nothing else. Let's shift enter here, and as you can see, we have a regular grid of our Bouguer residuals. And I don't want to jump into the interpretation. I want to make one more step before we jump into that, is to show you that as you can see, the data, the grid is pretty, it has a lot of information where on the areas where we had points, observation points. But here on the northwest portion of the grid, it's all very smooth. And the reason behind why this is smooth is that it's actually predicting, but we didn't have any data here. So it's not good to keep all these values as they were true, because I know they are not true. I'm sure that there's some awesome anomalies here, but because we haven't measured them, these values are wrong, right? So what we can do is to mask this value and set them to not a number. So what we can do is to use the convex hull mask function inside Verde, and let's see what the verde.convex whole underscore mask function has in its signature. It asks for data coordinates, that is the coordinates of the data points. So we are saying, okay, we are here on these points, we have data. And optionally, we can pass coordinates, grid, or a projection. So we'll stick to geographic coordinates here. So we will have to pass the longitude and latitude coordinates of our data. And we can just pass the grid, ignoring the projection, because the grid, it's actually in geographic coordinates already. So let's pass as first argument the data.longitude and the data.latitude inside the tuple. So they are one argument. And then the grid. And sorry, I have, okay. So what's the problem here? Oh, okay, sorry. I have to pass grid equal grid, and here data coordinates equal data coordinate. Sorry, I haven't read the error, but as you could saw before on the signature, the coordinates, grid, and projection are keywords arguments, so I have to pass them by the key. Okay, so now, oh, come on. Oh, made a typo here, coordinates. Someone will laugh about after this, I'm sure. So we have the convex whole mass that returns another grid. Okay, but now on the Bouguer disturbance, you can see that we had some not a number values. So let's override the grid we really had with this. And then we can see the grid here. And now let's plot this the same we did before. Grid.Bouguer disturbance dot plot and plt get current axis dot set aspect to equal. And run this cell. And as you can see, I have masked all these values that are outside the convex hull from the data points, defined by the data points, and set them to none. So I'm pretty confident that all the grid points we have so far have accurate values of Bouguer residuals. And I want to return to the geologic map by Susan Webb we had before here, where we could see the eastern lobe, the western lobe, the northern lobe, and this southern lobe that is not exposed to the surface. You can see that Susan and her team had made here a dash line. So have this picture in mind, and let's see the Bouguer residuals here. Sorry, here, the mass grid. You can see all the western lobe, sorry, the eastern lobe, the western lobe, the far western lobe, the northern lobe, and also we can see through gravity the southern lobe that is buried within the Earth's surface that is not exposed. So we managed to actually get Bouguer gravity residuals that could be interpreted to see and to give more insight about the object we have buried in the surface. So hopefully you don't have too many questions, and if you do, please ask in the Slack. And I have 15 minutes more, so let's jump to the final part that I promised. So the final part of this tutorial will be to extract a profile. Okay, so one way to do that is to, once we have this grid, is to actually set a pair of points and say, okay, let's interpolate between these 2 points with a linear interpolation, for example. Yeah, that's something you usually see in potential fields. But we already fitted an equivalent layer, and we could use this layer to predict the field values on each one of the points along a given profile. Okay, and we actually can do that through the equivalent harmonic class. It has a method called profile. Okay, that we can explore by Shift-Enter and see the signature. And it asks these 2 points, the point 1 and point 2, that define the beginning and the end of the profile, respectively. The upward coordinate of these 2 points, so we will define them at the same height. And then the size, that would be the number of points that are defined in the profile. And one thing that we should pass is that this profile is computed in Cartesian coordinates, so we have to pass a projection. Okay, great. So what are we going to do is to first define the point 1 and point 2 coordinates, and then after that I will run the profile. So let's create a new cell here and define point 1. Oh, sorry, point 1. Yeah, after 2 hours, my typos are very frequent. Okay, so let's define a point 1 on on the latitude on the longitude 26. That will be here, and latitude minus 25. And we want the profile all along the minus 25 latitude up to the 31 longitude. So we want to extract all the profile along this line. So let's define first the longitude, that would be 26, and the latitude minus 25. And for the point 2, I can use the 31 longitude minus 25 latitude. Let's use this cell that we had here, the code from this cell, and let's plot the same figure we had here, but also with these 2 points. So I can use plt.plot, and I could pass as the x coordinates the first element of point 1 and the first element of point 2. And in the y coordinates, I can pass the second element on point 1, that will be point 1, element 1, and point 2, index 1. Okay, so I'm setting 26 and 31 as the x coordinates, and minus 25 and minus 25 for the y coordinates. And let's use as a symbol the 1O and a dash. And that's it. Let's see what happens here. We can plot the profile we are about to compute with the first point and the last point of the profile. And let's jump into actually computing the profile. So I will define profile equal EQL profile. And what we can do here is passing first the coordinates of the first point, point 1. Secondly, the coordinates of the second point, point 2. The upward coordinate where we want to compute the profile. So that would be the height of the profile points. So let's use by upward, let's use the same 2,200 meters height. And let's define this profile of 200 points. Okay, so this profile will have 200 points. And one thing I would like to change is the data name. So I put data names equal to a list with Bouguer underscore disturbance. Sorry for the typos. And finally, but it's very important that I have to pass the projection, because this profile is made in projected coordinates. So I have to pass projection equal projection. And let's see what the profile has inside once we run this cell. Okay, that was very quick. As you can see, the formal are quick. Okay, the most demanding portion is fitting the equivalent layer. So that's why once I fit an equivalent layer, I want to use it for every task that I can use it for. So the profile has it's a data frame, it's a pandas data frame with northern and eastern coordinates. As you can see, all the northern coordinates are -25. So as you can see, these are northern and eastern coordinates, but it should be longitude and latitude. And so we can change that with, I think, dims. Sorry, I have to, dims equal to, remember, in this case, we have to put, latitude and then longitude. So, project. Why is, here. I missed a comma here, and now we can see. Okay, so the latitude of the points would be -25, and the longitude would change, okay, along the profile. And here we have the distance in, the distance in meters between each one of the points in the profile, along with the elevation of each one of these points that is constant, and the actual Bouguer disturbance predicted by the equivalent layer. Remember that I haven't used the grid to generate this profile. I just use the equivalent layer, okay? So let's plot these results by using matplotlib, okay? So we can use plt.plot, and let's pass in the x axis, I will pass the distance, profile distance, and then the profile Bouguer disturbance as the y-axis, okay? And let's plot this right away to see what it looks like. So you can see that it has the up and downs, but let's improve this plot before we jump into interpretation. So we can change the aspect, the size of the figure. So we can put plt.getCurrentFigure and put set size inches to, let's put 10 inches and 3 inches, so we can make it wider. And we can start adding some labels. For example, the X label would be distance, and the units are meters, and the Y label, are Bouguer residuals that are in milligal. And we can start doing a lot of this stuff if you want to make it look prettier. But I want to show you that along this profile we created before, we have all the up and downs of going across all these low disturbance and the high disturbance, low disturbance and the high, low and high. So that's one. I think that's what I wanted to show to you about the profile. We can do a lot of stuff from here. We can put the other plot beneath and make some comparisons. But I will leave that to you, and I will just want to share you how we can store all these results we obtain, so we can share this. We can share them to any colleague through a very neat and open format. So, for example, all the data frame we obtained throughout the notebook. Remember that it started with only 4 columns, and we have added a lot of other columns. So we can store this data frame directly with pandas, because this is just a pandas data frame. So we can put data.to.csv and then put the file name. That would be South Africa, for example, South Africa gravity disturbance.csv, and right away I can save it into my disk. I have it right here. Good to go. You can. It's a CSV, as the ones you are familiar with. So you can share that, upload it, put an open license, and let anyone use it. And also you can save the grid we created. The grid, that's an XArray dataset, into a netcdf file, which is an open format also. and anyone that has Xarray installed in their Python distribution can open it. You can use netcdf files for plotting on GMT, that the generic mapping tool. So you can share it, okay? So let's put grid.to netcdf, and then just put the name of the file we want. So South Africa residuals.nc, because it's a netcdf file, and run this cell, and it's storing this. I can refresh the list, and I have it right here. And that's ready to be shared, uploaded, add an open license like CC BY, and you're good to go to share your data. So that's all. Thank you very much for hearing me during 2 hours. If you want to know more about Fatiando project, you can visit the website, fatiando.org. I told you that you cannot run EQL Harmonic on a large data set, but hopefully, not hopefully, we have a new method that might change that. We have submitted a paper to Geophysical Journal International, and you can read the preprint that is right here. You can go into the comgeolab.org website and find the latest publication. It's under peer review, so we hope to be released soon and be available to anyone. So in this work, we have managed to develop a new method that allows us to fit 2 million points in a decent computer with 16 gigabytes of RAM. And if you're interested in that and you don't want to read the whole preprint, next week I'll be presenting a summary, the EGU 21. So if you want to jump in there, I will be presenting that. And Leodia will be presenting also a Pico talk on Harmonica and Boule. So if you are more interested in how the project works and everything, you can go in there. And finally, I want to say that we want your help. And seriously, we want your help. And you don't need to be an expert coder or software developer to help us. You can do a lot of stuff like submitting bugs, reports, and request features, bring use cases, writing tutorials or examples. You can, if you read through the documentation and find typos, you can improve that and help us to make it clearer and better. And if you feel like you could write code, please come. We have a lot of good fair issues. So if you want to check them out, please visit fatiando.org, and it's everything there. So just a reminder, I would love to see you tomorrow in the Chateau. That's tomorrow Friday at 11 a.m. GMT. I'll be there. I don't know, maybe we can pick a table or something. So thank you very much, and thank you for your time, and thanks again, Matt, for hosting. Thanks, Agustina and Andrea, for answering all the questions. I think that Leo's around there also, so thank Leo, and obviously thanks to all the open source developers that without their work, this wouldn't be possible. So thank you.
Amen. Yeah, great. Thank you very much, Santi. Great job. Thanks everyone for watching. One more tutorial to go today. We've got lightning talks tomorrow, Friday. Thanks for being part of Transform.
Thank you.